I'm Rob Davis from Mellanox, and I'm going to be explaining an exciting new storage networking technology called NVMe over Fabrics. So I want to start off with why do we need a new storage networking technology? Hopefully I can switch slides here, I guess not. Green button, right? Towards the speaker? There we go. No worries. So why do we need a new storage networking technology? We already have Fibre Channel. We already have iSCSI. And the answer is actually pretty simple. It's because in the last 5 years, storage has gotten a lot faster. Not just a little faster, a whole lot faster. In fact, if you look at the comparison of how much time it takes to access a hard drive compared to the persistent memory that was just talked about in the earlier presentation, 10,000 times faster. 100 times faster just going from hard drives to SSDs. A scale on the y-axis here is logarithmic. To put this into perspective, think about the distance from here to New Delhi. I think it's like 2,100 kilometers. I think in miles, so it's a little over 1,000, or over 1,000 miles. Now think about the distance from here to the airport, actually half the distance from here to the airport, because to the airport from here is about 20 miles, so 10 miles, about 15 kilometers, I think. That's the difference. That's the magnitude and the difference in performance we're talking about between hard drives and SSDs. I think Google says it's 35 hours from here to New Delhi, and it's an hour, or in the case of halfway, 30 minutes. So it's 34 hours or 30 minutes. A hard drive, 34 hours. An SSD, 30 minutes. This is huge, and this is just going between hard drives and SSDs. If you add persistent memory to this scenario, think about that lake that's about 500 feet down the road. Probably take 5 minutes to walk there. 34 hours, 5 minutes. That's the magnitude of the difference in the performance between hard drives and persistent memory. And that's why we need a new storage networking technology, because Fibre Channel iSCSI was designed for the drive all the way to New Delhi. So NVMe over Fabrics starts out with NVMe technology. NVMe technology has been talked about in quite a few presentations previously. Basically, it's a redesign of the interface to SSDs to get around the legacy interfaces that were used initially, the SAS interface, the SATA interface. And they did a great job. The performance is more than doubled, both in latency reduction and in performance. This chart shows the difference in performance between a Samsung drive that has a SATA interface on it versus an NVMe interface where the back end, the interface, the NAND channels is all the same. So NVMe over Fabrics was basically the next logical step because you had this great technology designed for local NVMe. Now you want to put it across a network to get all the advantages of a storage network, all the things SANs were invented for. Better utilization of the storage, better ability to manage it, better fault tolerance, all the things Fibre Channel SANs and iSCSI SANs have been doing for a long time. So a new standard was developed. It's done by the same organization that did NVMe, the NVMe.org. Everybody in the storage industry was part of it. My company, Mellanox, had architects work on it. It was released in June of 2016, but there were actually pre-standard demos done before that. This one was done in April of 2015 at the NAB conference. The company, the startup that provided the storage was called Mengstor. They've now renamed themselves, I think they're Nextend. And it was using InfiniBand and Ethernet technology, 40 gigabit Ethernet. Nowadays, the performance is much, much better. This is a chart showing one of our ConnectX adapters doing NVMe over Fabrics, and you can see basically wire speed and very high IOPS until you hit the wire speed. By the way, whenever you see these performance numbers, I know a lot of them have been shown across NVMe over Fabrics and NVMe. You have to keep in your thinking that the configuration here can make a huge difference. What the speed of the network is, what the technology of the network is, what your configuration of your PCI bus, the SSDs, a whole lot of things go into these numbers, and so they vary a lot. So NVMe over Fabrics is very unique in that it's not tied to any one wire. So Fibre Channel is tied to the Fibre Channel wire. SAS is tied to the SAS wire. NVMe over Fabrics, you can run it on any wire. It's very unique. It has this disaggregation between the actual protocol and the wire or the transport layer that it's running on, called the transport binding spec. And so you can have any network connected on it that you want to. RDMA was done first, so the first standard that came out in June of 16 was over RDMA. There's 3 flavors: InfiniBand, Rocky, and iWarp. Fibre Channel was done, I think, last year or early last year. And now the latest one that's just come out is NVMe over TCP. So how does it maintain the performance? The goal, in one of the presentations earlier this morning, they talked about the goal of NVMe over Fabrics was to be within 10 microseconds of the performance of a local NVMe drive. And it does that by basically keeping the same commands. So the same commands that are used to talk to a local NVMe drive are just encapsulated and sent across the network and de-encapsulated and presented to the remote drive. So there's no protocol translations that occur. It bypasses the legacy stacks, the legacy iSCSI stacks or Fibre Channel FCP stacks. And the first products were all done with RDMA, so the very highest performance was done first. And the performance is actually very impressive. This chart is public. All of the performance data I'm going to show is public. And it shows that you're within 20 microsecond of local performance versus RDMA, and 4 times better than iSCSI with SAS. If you look at NVMe over TCP, and this is actually the source of these numbers, about twice what you get with RDMA, but still half again is the speed of the iSCSI. So very high performance. Fibre Channel sort of sits in between this number. It didn't come from that same article. It actually came from a presentation by, I think it was Broadcom at Flash Memory Summit last year. But Fibre Channel kind of sits in between. But latency isn't the only thing to think about here, because bandwidth is super important with these SSDs. They can produce a tremendous amount of data very quickly. So with this faster storage, you need a faster network. And this chart is showing how many hard drives it takes to fill different speeds of networks. So you've got in yellow 40 gig, red is 10 gig, and I think it's supposed to be royal blue. It kind of comes out black here, is 100 gig. So if you're using hard drives, 10 gigabit Ethernet, this chart shows, is fine, because the sweet spot for JBODs was 24 drives. But all you do here on this next chart is I'm switching from SATA from the hard drive to the SSD, still using the same SATA interface, and all of a sudden 2 of them fill 10 gig. And that 24 gig sweet spot now is 100 gig. So what's happened is the bottleneck has moved from the media to the network. If you've got a storage networking application that's got more than 2 SSDs in it, and you've got a 10 gig interface, and you have fairly efficient software, you're wasting money on more than 2 SSDs, because you can't get that data in and out of your box with 10 gigabit. If we throw NVMe into the picture, 4 NVMe SSDs will almost fill a 100 gig link, and that's today's speeds. Tomorrow the SSDs will keep doubling probably every couple of years. If I throw Fibre Channel on there, you see, even though Fibre Channel has pretty good latency, the fastest Fibre Channel you can get today is 32 gig. So if you've got more than 2 NVMe SSDs in your Fibre Channel all-flash array, you're wasting your money on those SSDs. Luckily, at least with InfiniBand and Ethernet, there's plenty of bandwidth. Multiple companies, not just my own, we're shipping all the way up to 400 gigabit on our switches and 200 gigabit on our adapters today, but there's other companies doing the same, at least all the way to 100. So the wires are in good shape. But the wire is only half the problem. This chart, also logarithmic, but it shows the access time compared to not only the wire speed, which is in green, but also the software stacks involved in organizing the data and controlling that network adapter. And it compares the amount of time spent in that network stack to the access time of a hard drive. If we go to an SSD, you can see it becomes much more significant. And with persistent memory, it's about equal. So we not only have to get faster wires, but we have to get faster protocol. And that's where RDMA comes in. RDMA is the networked version or the remote version of DMA. Probably most of you know, but for people that don't, DMA is called direct memory access. It's an engine in all CPUs that moves memory from one location to another without sitting in a software loop doing it, one word at a time. So it's a hardware offload engine for moving memory. What RDMA is a remote version of that. So instead of the engine being in the CPU, it's in the RNIC, in the NIC that supports RDMA, and you give that RNIC a pointer and a location, remote location on the remote RNIC, and a pointer in the local memory, and it automatically, without any interaction with the CPU, moves that data. It's supported across Ethernet with Rocky and iWarp, across InfiniBand and OmniPath. And basically what's happening is that the transport layer that usually sits in the TCP stack or in the operating system kernel is now moved into the hardware of that NIC. So there's no CPU interaction at all to move that data. And that, of course, gives you not only higher bandwidth, but also much lower latency. And quite importantly, it removes, it gives you back a whole lot of CPU cycles that you used to use to move your data. And what do you buy those CPUs for? Probably not to move data, probably to run your applications. This is kind of the best numbers I've seen. It's using, I think, InfiniBand. And it, with RDMA, you can see 3 microseconds of latency. So very, very low latency across the network. That's both the request and the response. And high IOPS, and super interestingly, if I can get the pointer to work here, you can see almost 0 CPU utilization. You might think RDMA on Ethernet is kind of new because it's been around for a long time in InfiniBand, but actually it's already supported by all the major operating systems. I'm not 100% sure VMware is shipping yet, but they've made announcements about it. They've done lots of demos. I just don't keep up on the different version number releases of VMware. But it's in Windows. It has been for a few years. It's in Linux even longer. And there's large hyperscalers using it. And most hyperscalers are very secret. These two have actually made public announcements that they run their data centers on RDMA. Microsoft has been doing it for quite a few years. And if you look at the acquisitions some of the other big guys have done, draw your conclusions. Most of them are running on RDMA. That's because of the consistency of the bandwidth, the ability to manage the congestion and to know what your latency is going to be. So NVMe works very well with RDMA because the interfaces to an RDMA adapter and an NVMe SSD are very similar. They both use submission completion queues and RDMA or DMA to move the data. So if you look at how it's done with RDMA, the encapsulation process, you can see that the host driver is putting in the submission queue NVMe command that's then encapsulated into the RDMA send queue. That then goes across the network into the completion queue or the receive queue on the remote RNIC, which then takes it, then the NVMe or Fabrics stack then takes that and puts it into the NVMe SSD on the remote end. If you want to see it from a network perspective, over here on the left, it's hard to see this pointer, but over here on the left is the NVMe initiator that's posting the command into the submission queue. It's then encapsulated, sent across the network, put into the completion or the submission queue of the remote NVMe SSD. In this case, it's moving data. Reads and writes are always screwy in storage because the writes actually come from the storage side. But here, you see the RDMA writes, then moving the data. Once the data is moved, that completion message that came from the remote SSD is sent across and put into the buffer of the driver. So latency is super important if you want to maintain that low, that performance of the NVMe SSD. This chart is similar to the one shown earlier by the Intel presentation, and you can see on the far left is the hard drive. This is again a logarithmic scale, and then these would be like ZNAND from Samsung, as well as the new SSDs using the 3D crosspoint that we just were talking about. And then here would be a standard NVMe SSD and a SATA SSD. The issue is with networks is that most networks weren't designed like InfiniBand is designed, with low latency in mind because it's running a supercomputer. Most of them were designed around hard drives to move, to do general purpose networking. And so the latency typically between the adapter and the switch is about 10 microseconds. So if you're using NVMe over Fabrics with an Optane SSD, you've basically wasted your money because you've doubled the latency just crossing the network. Some companies, maybe mine, came from the world of InfiniBand, and so their designers are used to designing for low latency. There's other low latency equipment out there from other vendors as well. But the important point here is you want to make sure, if you want to get the most performance out of your NVMe SSDs, that you use a low latency network to connect them. Now there's another factor here, and that's that most networks have multiple hops. So that 10 microseconds triples. And this is storage, so it's a request response situation. So now it's doubled again. So now you're actually up to the latency almost of a SATA SSD, just crossing the network. So you got to be really careful of your network if you want to maintain the performance that's talked about for NVMe over Fabrics. Why this latency is important? Because one of the main applications for NVMe over Fabrics in the hyperscalers today is what's called, has many names, composable infrastructures, compute storage disaggregation, rack scale. What it all means is you take the storage and the compute apart, and within the rack, you disaggregate that compute and storage. And the reasons have been talked about in other presentations here is because you can get much more efficient use out of that compute and out of that storage because now it's networked. And in order to maintain, in order to make sure that any application you put into this environment, into this architecture works, you want to have as close to the performance of a local NVMe SSD with the remote NVMe SSD. Another application is scale-out storage. I've thrown up a couple of names here of companies I know are public that are doing scale-out storage with NVMe over Fabrics. There's lots of companies doing it with iSCSI. These are the ones doing it that I'm aware of with NVMe over Fabrics. Then there's hyper-converged nodes where you take that storage application that's clustering the NVMe drives into a pool and you put it in a VM. Again, what NVMe over Fabrics provides here is that same local performance across the network. What it means for hyperconverged infrastructure players is that you can now put high-end applications that require very low or very high performance SSDs onto your hyperconverged cluster. Another major use case, and Pure actually has a lot of blogs on this. You're going to see this out of a lot of other storage vendors over the next couple of years. Wick.io is another company doing it, and VAS. I'll talk about them more in a second. But this is a back-end storage network. So the front end is the standard iSCSI or Fibre Channel, maybe IB if it's like DDN or network appliance. But behind the scenes, there's another network that's based on NVMe over Fabrics. Like I said, Pure has a lot of good blogs on this. Their back-end network is all NVMe over Fabrics. What Wick.io and VAS are doing, is they've actually redone the file system in the case of Wicca and the object system in the case of VAS to take advantage of NVMe SSDs. A lot of times what you find in applications like you put these high-performance SSDs into your file server, but the file software is getting in the way, so you really don't see the performance. What Weka did was redesign the file system to allow that NVMe performance to get out. And that's the same with VAS. If you look at Ceph and you fill it up with SSDs, you get a little bit more performance, but most of the performance is in all that object software. What VAS did was redesign the object software to be higher performance as well. So NVMe in the classic SAN architecture just gives you more performance. So like a Fibre Channel network, like an iSCSI network, same architecture, it just runs a whole lot faster. And NetApp and Dell EMC have products out already doing this over NVMe over Fabrics. So there's offloads in NVMe over Fabrics just like in iSCSI, right? The TOE offload engines. What happens in NVMe over Fabrics without offload is you have a software layer. This is what NVMe.org did, which was really interesting, is when they released the standard, they also released open source initiator, target, and management code. And what it does is it basically, as the request comes in through the adapter driver passes it to the NVMe over Fabric stack, which interfaces to the block layer of the operating system, which talks to the SSDs. It's doing it through submission queues and completion queues that we talked earlier. And this is, even when you think about the fact that you're running millions of IOPS through this, it ends up using a lot of CPU and it adds some latency. What happens in the offload engines is you still have that target CPU software, but it's mainly just doing configuration and exception management. Inside the adapter is most of the function of that NVMe software, target software. So the adapter, because it's on PCI bus, is able to talk to the submission queue and the completion queue of the SSD and directly, and the data is moved directly from the buffers that the SSDs put it in directly out through the adapter on RDMA. So the adapter actually monitors the completion queue of the NVMe SSD until it sees the completion and then moves the data without any interaction of the CPU. And you can see the performance here. This is no offload. You're getting about 6 million IOPS, 2 million at 4K, and 15 microseconds of latency. With the offload, you're dropping that latency into the 5 microsecond range, and you're doubling or more than doubling the IOPS on the 4K blocks, just because you're removing that software from the loop. And if you look at what's happening on the CPU, basically it goes from 50% utilization to barely measurable across all block sizes. It starts to drop off as the block sizes get big, of course, on the CPU utilization. If you turn around that offload engine and put it on the adapter side, on the initiator side, so on the target side, it's taking NVMe over Fabric and converting it to NVMe. Here, it's taking NVMe and converting it to NVMe over Fabric. This is super important in that application that we talked about, the compute storage disaggregation, because those applications aren't used to working with stacks like NVMe over Fabrics. They aren't designed to work with network storage. Here, they think they're talking to local storage, and the hardware engine is converting it to remote storage. So the last technical thing I'm going to talk about here is NVMe over TCP. It's a really cool technology because it's really just an application, a sockets TCP application. And what that means is that you can basically support it on anything that has a TCP stack and a sockets interface. That's great because there's a lot of situations where you don't have RNICs, or it doesn't remote, or the protocol like Rocky or InfiniBand isn't designed to work over long distances. And because of the way the standard is written with the transport binding layer, you can run multiple protocols on the same interface because the upper level stack is totally independent of the protocol. The upper layer of NVMe over Fabrics is totally independent of what's happening below it on the transport. That's all based on the transport binding spec. So it's really great for things like distance. In fact, we've run it at Mellanox from our engineering labs in Israel all the way to our engineering labs in Sunnyvale, California, across the internet. and it works. Performance isn't great, but it works. And so for applications, storage applications that require geographic distances like high availability, it's a perfect solution. It's also great for what's called stranded servers. A lot of times when you put a new technology into a data center, you have some servers that are running mission critical applications, but no one wants to touch them because the guy that used to run it retired or whatever. And with this, you can hook those up to the NVMe over Fabric storage because it's just an application, and you can have RNICs on all the rest of your high performance or your new servers. And the last thing that it's really good for is out-of-band management. A lot of big data centers especially have a separate network for management that connects to the baseboard managers and all the servers. It's usually a lower speed network. It's usually connected to what's called a BMC or a baseboard management chip. And those have no RDMA, for example, no Fibre Channel, for example. So what this allows you to do is add the NVMe management layer, NVMe-MI, over the fabric connected in that out-of-band network with TCP/IP. So NVMe over TCP is great technology, but it does have some limitations. And the limitations are in the consistency of its latency. So this is kind of a confusing chart, but the y-axis here is actually measuring the amount of time or the fraction of time that the latencies actually match up. And what you see, hopefully this pointer will work a little bit here. What you see here is the local SSDs and the local SSD read and write, the remote SSD with RDMA read and write, and the TCP read and write. And there is a difference in latency, of course, but what's more important to notice is that the RDMA read and writes track almost identically to the local SSD reads and writes. Now, at the high end, you'll see, because of things like garbage collection, that the remote SSDs, the local SSDs will trail off. And what happens to the RDMA? It trails off at the same time. But more than about 50% of the time, what happens is the TCP read and write starts to trail off. And this is what they call tail latency. Tail latency, isn't shown very well on this chart, but here's a chart that demonstrates it. And basically it means that outside of the bell curve, where the data falls outside of the bell curve, it looks like a tail. So what that tail latency means is that more than 50% of the time you start to get inconsistent latency. And this isn't just something we've discovered. Lightbits is a startup that's focused on NVMe over TCP, and their website shows this. So, basically average 120 microseconds, but not 1% of the time you get 50% more latency, and 0.1% of the time it almost doubles the latency. This is a problem for a lot of applications, especially in the cloud, where the cloud is trying to figure out how to sell you something or what to present to you next, or trying to decide what your security clearances are. And these are very latency sensitive, and they have to occur in a certain amount of time. In the case of trying to sell you something or an advertisement, if they don't get there in time, then they don't get paid. So now just where is this industry? So it's kind of more mature than you'd expect it to be at this time. So there's a laboratory in New Hampshire, UNH. It's been doing this for years. I was first involved with it in the early 90s for Fibre Channel. And what they do is they take their students, their grad students, and they give them the spec, in this case the NVMe spec, and they give them a logic analyzer, and they say, look at what's on the wire, compare it to the spec, and write a report. And twice a year, they get all the companies together, and they have what's called a plug fest. And it's all basically vendor neutral because these students are just students, right? And at the last one, or actually it was the one before last, about a year ago, because they have these every 2 years, all three of the vendors of NVMe ASICs were able to run at both ends of the wire, at 25 gig actually at line speed, so both initiator and target. So all the ASICs seem to work together with NVMe over Fabrics. So it's actually an important milestone, because for a technology to get widely adopted, the OEMs, the big end users, they want second source. And so you need to have multi-vendor interoperability. Of course, the analysts, they always show the hockey stick, but in this case, I think they're actually right. This is a projection from G2M. They've been looking at NVMe for a while, and I've separated out the NVMe over Fabrics component, and it's basically a $20 billion market by 2021. This, of course, includes, for a large part, the NVMe SSDs, but they project, or they actually broke out the adapters, and they say there's going to be, 1.5 million of those, and that doesn't even include all the ASICs in the appliances and the all-flash arrays. And all these companies are involved with NVMe over Fabrics. Most of them have announced products or announced that they work with products like the SSD vendors, and the ones that don't have products actually shipping have showed demos and made promises that they will have products, within 4 to 6 months. If your name isn't up there and you're doing NVMe over Fabrics, let me know and I'd be happy to add it to you. I just went off of the ones that I knew about. So, in conclusion, NVMe over Fabrics is designed to bring the value of network storage to NVMe SSDs. It's supported across many network technologies. The performance advantages that you see with NVMe SSDs are not lost with NVMe over Fabric, especially if you're using RDMA. And there's a whole lot of suppliers of this technology out in the market today, and it's not just when it's going to happen, it is happening. And I have plenty of time to take questions. Thank you.